Everybody get your fucking hands up.
From the previous video, we've already learned that the average velocity is defined as the change in the object's position, the displacement, over the change in time, and instantaneous velocity is the time derivative of position function. If at the time t1 the object has a velocity of v1 and at the time t2 its velocity is v2, then the average acceleration is defined as the change in velocity over the change in time. And when the change in time delta t approaches 0, the average acceleration becomes the instantaneous acceleration dv over dt, or the time derivative of the velocity. And since velocity is the time derivative of position, therefore acceleration is also the second derivative of position with respect to time. When the acceleration vector is in the same direction as velocity, it is known as acceleration since the magnitude of velocity is increasing, versus when acceleration vector is in the opposite direction of velocity, it could be known as deceleration since the magnitude of velocity is decreasing. Now we have learned the first two basic kinematic equations, that the velocity v equals to ds dt and the acceleration a equals to dv dt. So if we combine these two and cancel out dt from both equations, then we get the third kinematic equation, ads equals to vdv, that directly relates a, s, and v. This third equation does not involve time. These three are the most basic kinematic equations, although please keep in mind that there are only two independent equations since the third one is derived from the previous two. When you are solving kinematic problems, depending on what is given and what is unknown, it is up to you to decide what equations are the best to use. Let's look at some examples. Some problems are quite straightforward, like this one. The particle's velocity is given as a function of time. Initial position is 0. And we need to determine its acceleration and position at a time t equals to 4 seconds. Let's look at the first part, the acceleration. We have three basic kinematic equations to choose from. Our given information is that velocity is given as a function of time and we need to find acceleration. So we have v, t, and a, and naturally we want to use the second equation since this equation has all the variables of interest. So we start with this equation, substitute v with the time function, perform the differentiation, and get a equals to 2t plus 2. And this is the acceleration as a function of time. So at t equals to 4 seconds, we can evaluate acceleration to be 10 meters per second squared. And that is the answer. And for the second part of this problem, we need to find the position of the particle at a time equals to 4 seconds. Again, we have the same three kinematic equations to choose from. And since we have velocity as a function of time and we need to find position, in other words, we have the variables v, t, and s that we're interested in, so the equation that has all of these three variables is equation 1. So we start with this equation, substitute v with the time function, and rearrange. Integrate both sides. Pay attention to the lower integration limits here. We got these from our initial condition that's given. And after integration and rearrangement, we get the position as a function of time. Now we can evaluate the position at the time equals to 4 seconds to be 37.3 meters. Let's look at another example. In this problem, acceleration is given, but not as a function of time. It is given as a function of position. A equals to square root of s. And also, initially, both velocity and position of the particle are 0, and we need to determine the velocity and time when the position of the particle is 16 meters. Again, let's first look at the first part, the velocity. In this first part of the problem, we know acceleration, position, and need to find the velocity. Again, when we look at the three kinematic equations, we notice that the third one has A, S, and V, all the variables of interest here. So we start with this equation, substitute A with the position function, integrate both sides. Again, pay attention to the lower integration limits. These are from the initial condition information that's given in this problem statement. And after integration, we get this. Rearrange, and we get this, which is velocity as a function of position. And now we can evaluate that at position s equals to 16 meters, velocity is 9.24 meters per second. For the second part of this problem, we need to find the time when the position is 16 meters. If we look at the three equations again, here the variables of interest are acceleration, position, and time. And we notice that equation 2 can be rewritten as acceleration is the second time derivative of position, which relates these variables of interest. But since from the previous part, we already get velocity as a function of position, so we can simply use the first equation since it provides the relation of v, s, and t, and it can help us find time. So we start with this equation, substitute velocity with the position function we got from the previous part, and we want to move the term dt to the left side and move the term with s to the right side. And integrate both sides. Once again, be careful with the initial conditions. And after integration, we get this. And then we can do the evaluation to get the time. Here we have a time as a function of position. Normally, we would rewrite it to be position as a function of time. This is because time is always independent. Therefore, after rearrangement, we get the position as a function of time. Or we can also get velocity as a function of time, or the acceleration as a function of time. As you can see, acceleration does equal to square root of position s. From these two examples, I hope you start to appreciate how important it is to choose the best equation to use. So when you see a kinematic problem, don't rush and jump right at solving it, but instead, make sure to take a moment and come up with a strategy.